What's up guys, welcome back to a new video, and in this session we'll be focusing on motion diagrams, and specifically we'll be connecting the xt diagram with its corresponding velocity and acceleration diagram. I will be going over several exercises step by step, and as always these exercises start out quite basic and get progressively more complex towards the end, so feel free to skip around according to your own level. You'll be able to find the timestamps in the description or the comments below. Before we get into the first exercise, I want to take a few seconds to just state what I assume you have as knowledge for this video. First, a basic understanding of xt diagrams, which means going from a scenario to drawing an xt diagram. And if you are not sure how to do this, feel free to check out the video that I specifically made on this topic on my channel. The second is some notion of the graphical interpretation of derivatives. Now, this is not strictly needed to solve these exercises, but they give it a nice interpretation, which gives you some more understanding. So with that out of the way, let's jump into the first exercise. In the first exercise, we're going to look at the simplest case of all, just the case where you are moving uniformly in one direction. This means on an xt diagram, that the graph looks like this. It's just a slowly inclining straight line, meaning that the motion is uniform. And how you can see this quite easily is that the difference in motion that you traveled, so the increase in x between 1 second and 2 seconds, will be exactly the same as between 5 seconds and 6 seconds. So this increase in x is the same as this increase in x, which means that our motion is uniform. How do we now go through the velocity diagram from this simple case? So the velocity diagram is v plotted as a function of t. We see that when our motion is uniform, it means that we are traveling at a constant velocity. So this means that our velocity doesn't change in time. So it is just a constant in time, a straight horizontal line. What does this mean for our acceleration? Well, it simply means that we don't have any acceleration, because the acceleration is the change of velocity. And if our velocity doesn't change, and we can see that here on this graph, we don't have a change in velocity, then our acceleration will just be zero along the way. And this is a very simple introductory exercise to show how these exercises are going to work. Now, an interesting case, and the second exercise, is to compare this with non-uniform motion. So let's start with an xt diagram, so t and x. And now our motion is non-uniform, meaning that our velocity changes over time. This means that our graph will have this curve, so our graph will be curved. We can see how this is non-uniform motion by again comparing how x changes from second 1 to second 2 compared to how it changes from second 5 to second 6. Whereas in the previous case, this change was the same. Here we see that between second 1 and 2 we have very little change, but between second 5 and 6 we have a lot of change. So our motion changes with time. The more time goes on, the more distance we travel within each second. How does this now translate to our velocity diagram in time? Well, we know that our distance traveled in time changes over time, so it increases. So our velocity also increases over time. This means that whereas in the previous case our velocity at second 1 and our velocity at second 6 was equal, now our velocity at second 1 is notably different from the velocity at second 6. How does this now translate to our acceleration as a function of time? In the previous exercise, our acceleration was 0 because our velocity did not change in time. We had a constant velocity. Now, however, our velocity does change in time. Velocity at the first second is notably less than the velocity at the 6th second. This means that our acceleration is just a constant. Let's now go to a more involved example of drawing these diagrams. Let's consider the case that we are in our car and we are initially at rest. Then we start the engine, we ramp up the velocity, we cruise a bit at a constant velocity, and then we decelerate and come to a halt again. So how does this scenario translate into an XT diagram? Let me draw this and then explain it. So this is how this graph should look. Initially, we are at rest. This means that our position, our X, does not change. That is this region of the graph. Then we decide to start up the engine and accelerate. So our velocity changes from 0 to a specific number, and that's this part of the graph. You see that our velocity changes. We are starting to move. Then the cruising phase is where we are moving at a constant velocity and not accelerating or decelerating. This is this piece of the graph. Then we decide to decelerate again, so hitting the brakes. And then we come to a halt and our X doesn't change anymore in time. So this is how the graph looks like on an XT diagram. Let's now see how this translates into a velocity diagram. So how does our velocity change in time? For the initial region, our velocity is 0, because before we start the engine and we start driving, our velocity is 0. Then our velocity increases, which is the green region, which means that we are accelerating. Then at some point we're just cruising at constant velocity, so our velocity is constant, so it's just a straight line at a specific value. Then we decide to decelerate again, so our velocity drops back again until we hit 0 velocity and we are just at rest. So this is how our VT diagram looks like. How does this now translate to our acceleration diagram in time? So we have time and we have our acceleration. In our initial position, we have 0 acceleration because our velocity is 0 and we're standing still, so our acceleration is 0 for this specific region. Then all of a sudden we hit an acceleration. Because our velocity changes, we have a accelerating period. Then we reach cruising speed, which means that we do have a velocity, but the velocity is not changing. So if there's no velocity changing, our acceleration is just 0. Then we decelerate, which means that our acceleration is negative because our velocity is decreasing in time. And then again, when we're at rest, our velocity is 0 and our acceleration is also 0. So this is how we can see this connection between these two diagrams. And let me just show where we actually have acceleration and where we don't. So in the blue regions and the red regions, we actually have no acceleration. Even though that in the blue regions we don't have any velocity, and in the red regions we do have a velocity, but it's constant. And in both of these cases we don't have acceleration. In the green region, however, we do have acceleration because our velocity is changing in time. This means that we have acceleration. Let's go to the next exercise to get a more feeling of how this goes. The second exercise considers the scenario where we just throw something into the air straight up and then let it fall back again. This XT diagram we know from physics, and I will probably do an extended video on this in the future, will be a simple parabola. How do we interpret this graph? We interpret this graph as throwing something into the air, then it comes to a rest, and then it just falls straight down again. And this point, this is an interesting point, because at this point we know that the velocity will be 0. Because at this point in time, the object that had an upward direction in the first half of its motion comes to a stop and then just falls straight down again. And if we look at the motion in time of this object, we see that it describes this very non-uniform motion. So it decelerates at the beginning, it comes to a halt, and then it accelerates again. How does this look like on our velocity diagram? Well, we know one point already, which is this point, where we know that the velocity has to be 0. It's this midway point where the object is stationary into the air. We know that it has a certain velocity when we throw it up, and that the velocity uniformly decelerates up to this stationary point. And then it just accelerates back towards the ground with the same change in velocity. How does this look on our acceleration diagram? Well, I already said that the change in velocity is uniform. This has to do with gravity, that it pulls on everything with the same acceleration. How does this now look on our graph? Well, initially our object has a positive velocity, but then it decelerates, so the velocity decreases, which means that our acceleration is actually negative because our object decelerates up onto this special point from which our object starts accelerating again, which gives it a positive acceleration. And the value of this acceleration in the second part and this first part is actually the same, but just with opposite sign. And this basically shows how these three graphs are connected. And you might now say that this is quite a trivial exercise. Why did I choose this exercise? Because now we can look at how these three are connected with each other when we look at derivatives. And therefore we need two ingredients. First, we know that the derivative of x to time is just the velocity, and the derivative of the velocity to time is the acceleration. So that's the first ingredient that we need. And the second is that the derivative is actually the slope of the curve. So what does this actually mean? Let's look at this first example. We see that the slope at this special point is actually 0. So the slope is 0 here. What does that mean? It means that the derivative of x to t in this point is 0. And what is the derivative of x of t? It's just the velocity. And if the velocity is 0, well, we did that right here. At this point, the velocity is 0. The same can be done going from here to here, because at this part of the graph, we see that all of our slopes are equal to each other, because this is just a straight line, which means that if the slope is constant, that our derivative is actually a constant. And here, because we are going downward, so the slope is negative, we see that we have a negative acceleration. The same goes on in the second part, where also all the derivatives or all the slopes in each point are positive, which means that we have a constant acceleration and it is positive. And this is how you can quite easily see how these graphs are connected through their slope, so through their derivatives. Let's look at the last exercise. This exercise is actually a bit more involved, but basically builds on the previous one. And what's more, it's quite an interesting case because it's more physically involved. The scenario that we're looking at in this case is simply letting loose of an object, well, preferably a bouncy object, and letting it go out of the window of a, for example, 2-story building. It will fall straight down to the ground, and when it hits the ground, it will bounce back. However, we know from experience that it will not bounce back to the same height as before. This is because some of the energy that went into the ball accelerating is lost to the ground when it bounces. So it bounces back and then comes to rest again. Then it just falls back down and it bounces back again, not to the same height, and it goes back down and so on. You know how it goes until in the end it just lies there on the floor and it's done bouncing. How does this look in an XT diagram? Initially, the object starts from a specific height, and then if we just drop it, it will follow this parabola trajectory all the way down to the ground. When it bounces back, it hits the ground and it goes back up again until it reaches its maximum and then simply falls down again in the same sense as the previous exercise. Then again, when it bounces back, it goes like this and so on, until in the end it just drops still. There are a few interesting points to note here. First of all, the points where the velocity is 0. As in the previous exercise, we noticed that these points are where the object changes velocity again. It bounces back from the ground, comes to a halt, and then falls back again. And then these times where it comes to a halt, the velocity is 0. And also here at the start, when we're holding the object above the ground, it also has velocity 0. Now there's also these quite interesting points here where the velocity simply decreases instantaneously because a lot of energy is lost to the ground. The velocity that the ball will have when it bounces back will be lower than the velocity when it reached the ground. If this were not the case, then the ball would just bounce back forever and each time to the same height. How does this now look on our velocity diagram? Well, we know that our velocities will be 0 on these specific points. And let's also take this last one with us. We also noticed these special points where the ball will reach a sudden change in velocity. First of all, the velocity will be in the other direction. But second of all, as I mentioned, the velocity will have decreased instantaneously. How do we now connect these points? Let's look at this first part of the graph. Here, the velocity actually increases because we just let go of the object and it accelerates towards the ground. So it increases at a uniform rate towards the ground. Then when it hits the ground, all of a sudden, the velocity decreases, like I said, because of the energy loss in the bouncing process. But now from this point, the velocity actually decreases until it reaches this maximum height point. So how do we draw this? Well, first of all, we start again, but from a lower velocity, and it uniformly decreases towards this point. Then, at this point, we again start increasing when the object starts accelerating back towards the ground, and we get this uniformly increasing velocity. Now we see that this graph is very familiar. It's simply just this one that we had right here when we just throw a ball into the air and let it come down again. So it's just the same basically. Then again, from this point, our velocity decreases suddenly because of the bounce. And then we again get this shape of throwing something into the air. When it comes to 0 velocity, it starts accelerating back to the earth again. So we again get this graph here. And then the same goes again and so on until we reach a point of 0 velocity. How does this now look on our acceleration graph? And this is actually quite an interesting one. So we have t, we have acceleration. Let's also draw our points here so we have a nice overview of what is happening to our acceleration. And I see that I've drawn this graph too short, so we will just extend it a bit. And we also project the points of 0 velocity, and we can start thinking about the acceleration. In this first part, the object actually accelerates, so the velocity is increasing. So we have this, and it's increasing at an equal rate because gravity pulls at everything in an equal fashion. So the accelerating motion is uniform, so we have a constant acceleration. Then from this point, this red point here, we actually have the object decelerating again, because here it's bouncing up, meaning the velocity is decelerating or decreasing. So we have an equal acceleration, but now with a negative sign. Then, when it reaches its height, it starts accelerating again, meaning from 0 velocity back to the earth, accelerating in motion. Then until it reaches the bouncing point again, and it will decelerate again. And then accelerate, decelerate, accelerate, and so on. What we see here is that we have this alternating acceleration in sign, but always the same magnitude. And this is basically how these three graphs are connected to each other of something that is thrown out of the window and bounces up and down. This brings us to the end of the video, and I hope you learned something. Now, if something was not clear or you're confused about something, be sure to just leave a comment in the comment section and I will be answering you and helping you along the way. Again, if you really like this video, just give it a like so that people that are also looking for these videos are more likely to come across them. If you want to see more of these videos, you can always check out my channel. And if you want to get notified by future releases, you can just hit the subscribe button. And with that, I'll see you guys in the next video. Bye.